Yes, so we will listen to Emmanuel.
Stéphane.
Stéphane. Okay.
Stéphane.
Sorry. Puechmorel about canonical foliations of statistical manifolds with hyperbolic compact leaves.
Well, good afternoon, everybody. So this is a joint work with Michel Boyom and Emmanuel Gnandi. And I will present you some results about hyperbolicity for compact leaves of statistical manifolds. In fact, it will be results relating some characteristics of group representation to hyperbolicity. So the agenda of the presentation will be first a short introduction on the problem, then I will introduce the Hessian equation and its sheaf of solutions. Then we will go to the main point of the presentation, namely affine representations of groups. And finally, we will apply the main result to the leaves, the compact leaves, in fact, of statistical manifolds, and we will draw a conclusion at the end. So first of all, we all know that hyperbolicity is a very important notion in differential geometry. Here, we will be dealing with hyperbolicity in the sense of causal. So I will be a little bit more specific about that in the next slide. It is important to note that the hyperbolicity in the sense of causal is related to the development map. It turns out that in the case of Hessian manifolds, compact ones, the hyperbolicity can be related to a cohomology condition. In fact, it is equivalent to the vanishing of the second causal cohomology. So in the work here, we will present an approach using affine representation to find an equivalent characterization, in fact, equivalent to the cohomology characterization. And in fact, this approach will allow us to characterize hyperbolic leaves, compact ones, in fact, in canonical foliations of statistical manifolds. Well, first of all, a locally flat manifold equipped with a causal connection, nabla, is called hyperbolic if its universal covering is isomorphic to a convex domain not containing any straight line. The diffeomorphism used here is the development map introduced by causal. So the definition is through inverse parallel transport, but there is quite a simple picture of the development map. You can imagine you simply draw a path on your manifold, you fix a point, you consider the tangent plane at the point, that point, and you make the manifold roll without sliding on the tangent plane. So it is an intuitive, of course, picture of the thing. And if you look at the endpoint on the tangent plane, then it is just exactly the development map. So the development map, in fact, will associate to a path, but in fact can be proved that it is simply the homotopy that counts. So you can associate to the homotopy class of a path a point in the tangent space at a given point, a distinguished point. Okay, so hyperbolicity condition for a locally flat manifold can be obtained also using a cohomology condition, and the cohomology condition is the existence of omega, a one form, such that nabla of omega is positive definite. And when manifold is compact, it is also a sufficient condition. Now, we go to the cohomology condition related to hyperbolicity. So first of all, I prefer to go straightly to the theorem. We will, in fact, introduce the causal-Weinberg complex later. This time, we consider a compact Hessian manifold, meaning that we add a metric, G, to the structure, and the metric has to be an Hessian one, has to derive to the Hessian of a potential function. Then in such a case, you have a set of two equivalent assertions. The first one, that is the cohomology condition, is the vanishing of the metric tensor in the Kosul-Weinberg class, in fact, the second one. And of course, it is equivalent to M nabla being hyperbolic, again, in the sense of Kosul. So just looking at the Kosul-Weinberg complex, so the definition is not so intuitive. But anyway, there is something that is worth to be noticed. It is the fact that if you look at the co-boundary operator, and namely at the sum occurring in the right-hand part, you see that the nabla, the connection, is acting more or less like a product. You see that we contract, in fact, one of the xj using nabla xi xj. And this can be made more apparent by considering the Hessian equation. So this time, for the moment, we drop the metric structure. We consider only the gauge structure with M and the causal connection. And the Hessian equation is just nabla square of x equals to 0. So basically, it's a solution that is local. So we want to consider the sheaf of solutions that is defined to be simply the association between an open set U and a set of local sections over U such that nabla square of x is equal to 0, meaning that it vanishes identically. This time, we use the connection as a product, meaning that to a couple xy, so here we introduce, in fact, global sections, but it works, of course, for local sections. The product is just lambda x y. It is interesting to remark that the pair consisting of the solution and nabla as a product is an associative algebra. And in fact, the commutator is the bracket. So it is something very interesting, because if the connection is torsionless, then the bracket just defined is just the usual bracket between sections. And in such a case, when the connection is torsionless, then the real Lie algebra is finite dimensional. This Lie algebra may be trivial in some cases. It is in particular the case of Einstein manifolds when you take the Levi-Civita connection as the base connection. Finally, if you invoke Lie third theorem, then you can find a unique simply connected Lie group. So that will be denoted G nabla in the sequel with Lie algebra isomorphic to J nabla. Okay? Now, we proceed to of interest for us. So first of all, let me just recall that if you consider a real finite dimensional vector space, its group of affine isomorphism is a direct product, a semi-direct product, that is the product of the linear group by the group of translations. In the presentation, we identify the vector space with its group of translation. It's an abuse notation, but a very classical one. So first of all, we start with a representation, but here as a Lie algebra, a vector space of J nabla into the set of small a, so it's not affine isomorphisms, but just affine representation of J nabla. And you see that, in fact, the representation is quite simple to understand. You have a translation by a section X, so you consider a fixed section X. You have a translation by the section X and a product with nabla X. Once again, we can extend uniquely this representation as Lie algebras to Lie groups, namely J nabla. So this time, the representation belongs to the group of affine isomorphisms of J nabla. So to summarize things, this procedure allows us to define a continuous affine representation between J nabla and the group of affine isomorphism of G nabla. Here is the main theorem. So you have an equivalence between three conditions. First one, the affination as a fixed point. Second, it is a cohomological condition. And finally, the affine representation is conjugated to the linear representation. What is important is that you relate a cohomology condition to a condition on affination. In the case of statistical manifolds, we can take a step further, because if we consider a statistical manifold, then we can obtain a foliation related to nabla, or the dual connection nabla star, that is Hessian. And in fact, in a statistical foliation, in a statistical manifold, if you apply the previous result, you obtain the following theorem, asserting that we have a set of 4 equivalent conditions. So let's stop a little bit on the first one. The first one is hyperbolicity condition. If you look, it is the fact that you have a vanishing of the metric tensor. G nabla means that you simply take the restriction of the metric tensor on the leaves of the foliation. So first condition is, in fact, an hyperbolicity condition for the leaves. Second one is a cohomology condition. Third one is, and in fact, fourth one, are related to the group representation. We can slightly rewrite the theorem, and since we have a cohomology condition, and that is related, in fact, to hyperbolicity, we can use a result from Kosul about hyperbolic manifolds. And the theorem is the following. If you consider a statistical manifold, if you consider its canonical foliation, then if you have a vanishing of the characteristic absorption, the first one is the usual one, the second one is related to group representation, then up to an affine diffeomorphism, every compact leaf yields the quotient of a sharp open convex cone by a discrete group of GL Rn. So it means that, in fact, you have a structure theorem for the compact leaves of the canonical foliation of the manifold, provided, of course, that the compact leaves are hyperbolic or satisfy the absorption that is the same. So, to conclude, first of all, we have a characterization of hyperbolicity in terms of affine representation. The interest of the characterization is not to obtain something that is just another formulation of hyperbolicity, but the fact that from it, we can derive some results about the structures of hyperbolic compact leaves in statistical manifolds. It turns out that, in fact, due to the previous result, in dimension 4, you have a classification of compact leaves. And finally, in a future work, we will use the result about foliation to equip a statistical manifold with a foliation by statistical models. In fact, we will be able to put densities belonging to the exponential family on the leaves such that the metric tensor obtained by restriction on the leaves correspond exactly to what you have by considering the Fisher information associated to those particular exponential families. So I think it is the end of the presentation, and I thank you for your attention, and I'm ready to answer your question if needed.